In this video, we go beyond theory and simulate ARMA and ARDL models directly in Mathematica. We will generate artificial time series data, estimate dynamic econometric models, and examine how well the estimated parameters recover the true parameters of the data generating process. We start by clearing the workspace and setting a random seed for reproducibility. We then define the sample size, constants, and model parameters. We begin by simulating an ARMA 1-1 process in Mathematica. The current value depends on three components: its own lagged value, the current shock, and the previous period's shock. The autoregressive parameter controls persistence, while the moving average parameter controls how shocks propagate through time. Using these parameters, we recursively construct the ARMA series. Each observation depends on the previous observation and stochastic shocks. The resulting graph shows a dynamically evolving stochastic time series generated by the ARMA 1-1 process. Notice how the series exhibits persistence due to the autoregressive component, while random shocks create short-run fluctuations through the moving average component. Together, these features produce the characteristic behavior of an ARMA process. Next, we estimate the ARMA model using Mathematica's TimeSeriesModelFit function. Unlike ARDL estimation, ARMA estimation cannot use ordinary least squares directly because past shocks are unobserved. Mathematica therefore uses likelihood-based numerical optimization to recover the model parameters. The estimated process should recover values close to the true data generating parameters used in the simulation. We now compare the true parameters with the estimated values. Because the data were generated from a known stochastic process, we can directly evaluate how accurately the estimation procedure recovers the original structure. Small differences occur because of finite sample randomness. Notice that the estimates obtained from 200 observations are reasonably close to the true parameters, but some estimation error remains because of finite sample randomness.
To see the effect of a larger sample, we repeat the simulation and estimation using 5,000 observations. With substantially more data, the estimated parameters move much closer to their true values. The estimated constant is approximately 2.02. The autoregressive coefficient is approximately 0.694, and the moving average coefficient is approximately 0.414. These estimates are very close to the true parameter values of 2, 0.7, and 0.4. This illustrates an important principle in econometrics: as the sample size increases, parameter estimates tend to converge toward the true values used to generate the data. We now simulate an ARDL model with 5,000 observations. The explanatory variable follows its own autoregressive process, while the dependent variable evolves according to an ARDL 1-1 specification. Notice that we generate 5,000 observations but later discard the first 2,000 observations. This procedure is known as a burn-in period. At the beginning of the simulation, both variables start from arbitrary initial values, typically 0. As a result, the early observations are heavily influenced by these artificial starting conditions. By generating a long series and removing the first 2000 observations, we allow the process to settle into its long-run stochastic behavior before estimation begins. After removing the burn-in observations, the remaining sample is far less influenced by arbitrary starting values and more closely reflects the model's long-run stochastic behavior. This produces a cleaner experiment and allows us to evaluate the estimation procedure under more realistic conditions.
Next, we construct the regression data set. The dependent variable is the current value of y, while the regressors include a constant term, the lagged dependent variable, the current value of x, and the lagged value of x. We generated a much larger sample for estimation, but for visual clarity we display only the first 200 observations. This graph shows the dependent variable generated from the ARDL11 model. Unlike the ARMA process, the behavior of the series is driven not only by its own past values but also by the current and lagged values of the explanatory variable. As a result, the ARDL model captures both persistence within the dependent variable and the dynamic influence of external economic factors. This is precisely why ARDL models are widely used to study short-run dynamics and long-run economic relationships. We then estimate the ARDL model using Mathematica's linear model fit function, which applies ordinary least squares estimation. Because all explanatory variables are observable, the coefficients can be estimated directly through regression. We now compare the estimated parameters with the true values used to generate the data. The recovered coefficients are remarkably close to the true parameters. This exercise is known as parameter recovery and is commonly used in simulation studies to verify that an estimation procedure works correctly. This demonstrates that with a sufficiently large sample, OL's estimation can accurately recover the underlying ARDL structure. Finally, we compute the long-run multiplier. The true long-run multiplier is 6, obtained from the sum of the distributed lag coefficients divided by 1 minus the autoregressive coefficient. That is, 1.2 plus 0.6, divided by 1 minus 0.7, equals 6. The estimated long-run multiplier is approximately 5.94, which is very close to the theoretical value. This close agreement provides strong evidence that the estimation procedure has successfully recovered the long-run relationship embedded in the data generating process.